Hello, welcome to session number 2 in the series Clocking Circuits. My name is Anurag Nigam, and in this series we are talking about PLLs. And last time we had seen an overview of a PLL design and also the operation of some of the circuits. Now we are going to go into detailed design, and I will start with the basic operating principles. So now the first circuit which we are going to pick up is a voltage controlled oscillator. Okay, so there has to be a control, voltage which will control this oscillator, right? Oscillator frequency. Now the basic principle is as follows: there is a tank circuit or an anti-resonance circuit of this form, and it we know resonates at 1 over 2 pi root of LC. So this is going to be frequency of oscillations. Now we can choose L and C in the proportion we like, right? So as that we have 1 over 2 pi root of LC as the desired frequency, right? Now there is an issue with this. So if I, for example, if I charge this capacitor, okay, C capacitor, to a full voltage of, let's say, V peak, right? And right now I am going to just leave it as is. So what's going to happen is that this capacitor is going to discharge, right? This capacitor is fully charged, it's going to discharge, and once the voltage becomes 0, the current has reached the maximum. So basically the current build has reached the maximum at this point, right? Now the inductor has a property to resist the change of current. So this current is supposed to continue, okay, and this is what the current is going to do, right? And this causes the capacitor to charge in a reverse direction, to minus Vp, right? And this cycle basically continues. Now if, for example, there is an additional loss here which I call as Rp, right? What's going to happen is there is going to be a portion of current which is going to divide here, right? And this would be taken as a I square R loss. And when this happens, what's going to happen with the voltage waveform is it's going to damp out over a period of time, right? So these are your output waveforms, voltage waveforms, and the current is going to do the same stuff, right? So the current is also going to decay, right? So something of this nature, the current is decaying, right? So this decay which you are seeing has to be compensated, right, for the oscillations to sustain, right? So we have to overcome this loss, right? So now if I was to plot this like impedance, right? So if I was to plot this impedance here, right, for this tank circuit, what's going to do is, if I was to plot the impedance of this tank circuit, okay, so at the frequency of f naught, okay, so this is going to stay low at low frequencies because of the inductor, right? And at fc, that inductor reactance and capacitor reactance are going to cancel, or basically this is going to look like an open circuit, okay, and this should go to infinity, right? So this is asymptotic, okay, so this is going to go to infinity, and then the capacitor dominates, and this is going to decline like that. So that will happen to the impedance. Now because there is a loss associated, so at here it should look like, if I was just to take a RLC without the loss, then this would be infinity, right? But because of there is a loss, right? So that that resistance doesn't build to infinity, but it goes to a point and then it drops off. And this value is basically RP, right? Parallel resistance. So now this is what is happening. Now let's look at the nature of this resonance. Okay, if the Q of the circuit is low, then the waveform would look like this. But if the Q of this circuit is high, then the same waveform would look like this. So I hope you get it, that if the Q is low, what's happening, and if the Q is high, what is happening. So loss of the tank circuit becomes important here, right? And how would you make it to sustain oscillations? If I was to add a negative resistance in parallel to this, which is equivalent to minus RP. So if I had a minus RP in parallel to that, then this is equivalent to no loss, and the oscillations are going to sustain, right? Now, what is a circuit which is going to give me a negative resistance? So let's see an example. Let's say if I have an NMOS device and let's say have a voltage applied as small signal voltage as Vx, and this has a polarity as shown in here. Now if I cross couple a transistor like this, okay, and similarly I can go this way and cross couple a transistor like that, right? So if I do this, this can be a source of negative resistance. And how? Let me show you how. Now if I remove all the parasitics of the device, and this is a voltage controlled current source, then you are going to have a current which is in this direction, right, which will be equivalent to GM times of whatever is applied at the gate, and what is applied at the gate is minus of Vx, right? And then similarly the other side is also a current source which is going to be GM times of Vx. Now this direction is reversed basically, so the net current over here is going to be GM times of Vx, okay? And if it is an NMOS, I would add an N here. So I have a voltage Vx, and then I have a current which is GM times of Vx, which is Ix, right? So I can say that total conductance, okay, now this is a negative number, right? Okay, so because this is in the reverse direction to this polarity, plus and minus, right? So that's why it's negative. Now that means that my conductance is going to be Ix over Vx, which is going to be minus GMN, right? Similarly, if I follow this same analysis with a PMOS transistor, that is going to give you minus GMP, and the overall conductance would be GMN plus GMP with a negative sign. So this is the negative conductance which is offered, and this, okay, is in resistance would be 1 over that. And if I was to add RP to this, right, so that would be 1 over RP, okay? So if this is the situation, right, okay, then I am trying to approach an ideal case, and that ideal case is this infinity. So which basically means that this GMN plus GMP plus 1 over RP should tend to 0, right? Or RP should be equal to minus 1 over GMN plus GMP, correct? So if I was to apply a negative resistance, okay, and how do I apply that? With cross coupled transistors, right? If I was to apply that, okay, such that the negative resistance becomes equal to the loss. Okay, why am I writing RP? Because of parallel. Okay, so then that would be the relationship. Okay, so what does that mean? Okay, what that means is, okay, the circuit would look something like this. I would have a PMOS device and two PMOS devices which are going to be source some current. Okay, so they are source some current from the supply, and there can be a simple current mirrored means diode connected transistor over here to do that. And this is cross coupled here, and this is cross coupled here. Okay, so this is the PMOS. Then I have an inductor which is like that, and here if I want to vary the frequency of oscillations, then I am going to have two diodes which are varactors, which are connected like this. Okay, now let me explain a little bit about varactors. So there is a control voltage here. Okay, this is VC, and then you have got transistors, NMOS transistors like this, and they are cross coupled like this. Okay, so this would be called a VCO core, right? And the sizing of these transistors basically is to overcome RP, or I can say that they should be such that we have this relationship, right, which we have just derived, RP, right? We have to have that, or we can have even more than that, right? Now if I look at this circuit, okay, I have an issue here. Okay, so that issue is as follows. Okay, wait a second. Okay, the issue here is, if I assume that this current and this current are same, right, then the net voltage here and here is the same, and this is a stable state, right? So this current I1 and I2 are same, then this is one of the stable states, right? And that means that the net voltage across here is 0. So that Vx which we are seeing is basically 0. That means that there are no oscillations. So this core will not work if I don't have some form of a current impedance which is going to start the oscillations. So I need some form of a startup circuit. So to make a startup circuit, all I have to do is I will take a PMOS device like this and connect it to ground and connect a capacitor here, right, and connect this to supply, right. So what this does is, when I switch on this circuit, this capacitor stores a zero charge, or it's a 0 volt here, and then it charges through this voltage, right. And that means that at the turn on, this device is totally on. That means that it's going to pull the current out of here. So I2 becomes much less than I1, right. This causes the circuit to go out of that stable state, which is undesired, right. So this startup circuit is going to imbalance the currents I1 and I2 and start up the oscillation. So this is called a startup circuit. Now once the VCO basically has gone so into a steady state of oscillations, what has happened is this net voltage here is going to be VDD, right. So once this capacitor is charged, the net voltage here is VDD. That means that this device is now off and it is disconnected. It is disconnected from the, it is totally disconnected from this circuit. So once this circuit sets the VCO into oscillations, this circuit gets disconnected from the VCO core, and you have symmetric oscillations here because now the entire thing is symmetric. Now one way to assure symmetry is you lay out this transistor and this transistor as a common centroid, right, layout, and we will talk about what is a common centroid layout. Similarly, this transistor and this transistor is laid out as a common centroid, and they are equal in size, and in the layout also they are common centroid, so they are matched. Okay, now why is it important? Well, if you have these transistors balanced, right, a the noise will go down, because then the noise is differential, right, and that differential noise would basically cancel it out, right. So that is one reason why they should be matched. Another reason is that even harmonics, right, uh, they would be canceling out, right. So this circuit is balanced, right. So that's the idea. Now the idea is to compensate the loss of the tank circuit with these cross coupled devices. So to design it, okay, you can follow the rule of, the dumb rule of iteration, right, where you start with certain size of devices and do the simulation and figure out when the size are sufficient enough to make this oscillation to occur. Another is to figure out this component through simulation, and then decide what you want for GMN and GMP. Now in this choice also, you will choose GMP to be much larger than GMN. That means two things. Okay, so let's say this voltage is V2 and this is V1. So if GMN is much smaller than GMP, then V2 and V1 are going to be large. This provides a sufficient voltage across the device. So basically, what is the control voltage range? Control voltage range can go from 0, it can even go negative if you want, okay, can go from 0 to V2 comma V1, whichever want to take. Okay, so this is your control voltage range. So if I choose a smaller NMOS, that would mean that I can have a larger voltage across the device, and the capacitance basically is going to be of a reverse bias diode is going to be like this, right. It is going to go up and to a point where it is going to be 5/2, okay, where the device turns on. Okay, at that it will reach the maximum and then it will drop off. So this is basically what capacitance is doing, right. So if you have a large voltage, which is negative large voltage, VR is a large voltage, then the capacitance is small, right, and the device would tune to a higher frequency, f2. Okay, so VC is small, then it is tuning to f2, and then if VC is large, okay, VC is large, approaching this value, then it is close to 0 volts across the device, or 5/2 across the device, then the capacitance is large, then it will be tuning at f1, right. So this is 0, this is VC, which is going to be V2 or V1, whatever you want to take. Okay, so what does mean? It means that the VCO gain here is negative, right, KVCO. Okay, so now there are two more things. So let's jot this down or summarize this. Okay, so first of all, what did we see? We saw RP should be equal to -1 over GMN plus GMP. Okay, so this is first thing we had to prove. Second is we assume that GMN is much larger than GMP, which means that NMOS devices are small compared to PMOS devices, right. So what's the benefit of that? That benefit gives me 0 to V2 comma V1 as the tuning range. So basically this number goes up if the devices are large for a given current, right? And another thing is the devices, NMOS devices, are the source of what you will call uh, flicker noise, right? Uh, yeah. So NMOS devices are a bigger contributor of flicker noise compared to the PMOS devices, and the reason being that electron has a higher mobility than hole, and the relaxation time with the defects is much smaller. That means that the noise is is large, right? So that's the reason why NMOS devices should be smaller than the PMOS devices. So another reason is NMOS devices are noisier than PMOS devices. So that is the reason where NMOS devices should be as small as possible, and PMOS devices should be as large as possible. So this is one condition. This is another condition, right? Okay. Now the third thing I want to talk is RP should be maximized. That is, Q of tank circuit should be large. Now, what I mean by that is, if you have a sharp uh, response of ZP, which we have already seen, versus frequency, so this is at F naught, right? So if this is tall and narrow versus if this is fat and small. Okay, now this scenario will give me a much worse noise figure, or sorry, phase noise, while this scenario is going to give me much better phase noise, and I'll tell you why. Okay, so how is the current flowing? Okay, the current basically takes this route or that route. Okay, so current is taking these two routes when the current is swinging, right? And the current is basically drawn constant from here, right? Now this point, okay, at crossover, the two currents are same, right? So when two currents are same, okay, the net voltage across this is 0, and when the net voltage across a resonator is 0, okay, if when the net voltage across resonator is 0 and net current is 0, this circuit is more prone to perturbation. I don't know if my spelling is correct. Okay, so what I mean is, this circuit can be perturbed when the net voltage across the tank circuit is 0 and at the same time the current is also 0. Then there is an issue of perturbation across this tank circuit, and that perturbation, okay, has more range if this is less, this is more flat, versus when it is more peaky. So what I'm trying to say is, the circuit is going to perturb more, right, if the Q is basically less, okay, because this is being compensated by 1 over GMN and GMP, right? So basically you are using much larger transistors to compensate for much smaller RP, right? You are using much larger transistors to compensate for much lower RP, and that gives you a more probability of, you know, perturbation. Like, you know, perturbation is more here when you do that, versus when this is compensated by a small peak like that. So I hope you understand what's happening. What's happening is when you compensate uh, a high loss tank circuit with a negative resistance, okay, your bandwidths are large and the perturbation noise collected would be large, and that basically contributes to the phase noise of the VCO. So I hope you understand what is the significance of high Q tank circuit versus a low Q tank circuit. Of course, in both cases you can make the VCO to oscillate, but in one case the noise will be much larger than the other case. So this I hope you understand. Another way is to minimize perturbation would be if I was to place a tail capacitor here. Now what this tail capacitor is going to do is it is going to cause a certain DC value of current always through this inductor. That's what this C tail would do, and that causes a minute voltage to always be there, DC voltage or current always be there in the tank circuit, and that would basically minimize perturbation, right? So if you have a very lossy tank circuit, then it's beneficial to put a tail capacitor, and that tail capacitor is going to minimize the phase noise, right? So now this looks like a garbage, the way my handwriting is not good, but I hope I captured the essence of what the Q of the circuit is going to do, right? So this is basically Q should be as large as possible. That means that choose the tank circuit with now the question is whether inductance is lossier or capacitance is lossier. So we have to decide between inductor lossier or varactor lossier, and the varactor is usually lossier, okay, than the so varactor is lossier. Varactor is lossier than the inductor. So if you choose a large inductor and small varactors, you are going to have a better phase noise, okay. Large inductor and small varactor will result in better phase noise. Correct? So large inductor and a small varactor will result in a better phase noise, right? Okay. Now then again there is a trade-off here, right? If I choose a large varactor, okay, so the net capacitance across the inductor, okay, so I can say the net capacitance across inductor, okay, that is going to be a fixed value which is C parasitics plus C variable, right? Now if I choose a small varactor, this one is fixed, this one is coming from the output capacitance of the 4 devices, right? So C para is the output capacitance of the 4 devices, okay, so 4 devices, while C var is coming from the 2 varactors, and again these the net capacitance, okay, is the sum of the 2 varactor capacitances. Now that capacitance, right, that capacitance has to be maximized for the tuning range. So the other trade-off which comes is the tuning range. Okay, so tuning range, okay, basically is going to ask for a larger vector, while the phase noise, lower phase noise, is going to ask for a smaller vector, right? So now there is a trade-off between the tuning range and the phase noise here on this VCO core. Okay, so I hope I have covered that portion, right? So now we should jump into what you call the simulation to see this, and then followed by the design. So we know some of the trade-offs here, right? So let me see this, how much time I have spent on recording. 30 minutes. Okay, so in next 30 minutes I'm going to show you the design, right? Okay, so let's go ahead and look at some of the things. And here I have got same CMOS PDK for ADS and for Cadence, right? So this is a 130 nanometer process. So the ADS PDK is not available from the fab, but I have fitted the PDK. Okay, so let's go ahead and create a new workspace and say explore VCO, right? And I am going to attach a library which I call study PDK, which I have used in analog circuit design also, right? And say create a workspace, and micron is the layout resolution in finish, and I'm going to place these model files into another folder called it lib or just lib. Okay, and copy all of these into lib so that I don't alter them. Okay, I'm going to create a new schematic and say study tank. Okay, so I'm going to study a tank circuit. Okay, so here I am going to pick up an inductor, and okay, so okay, let's see if I'm recording it. Hang on, because I pressed some keys, I want to verify. Okay, is my mic on? Yeah, my mic is on. Okay, fine. So I'm going to take an inductor, and I am going to design something for a range. Insert text. Okay, I'm going to design something for a range which goes from 5.8 gigahertz to 7.2 gigahertz. Now this is basically going to be Wi-Fi 6E. Okay, and I want to create a VCO which is in the range 2/3 of that. So if I take a calculator, okay, so I am going to basically have an output stage which will do quadrature generation and will also up convert the frequency to 3/2. So I'm designing a 2/3 frequency of that. So standard calculator, so I want to look at 2/3 times of 5.8. Okay, so that is going to be 3.8 gigahertz. So I have to have a VCO which goes from 3.8 gigahertz to 7.2. So 7.2 divided by 3 multiplied by 2, that's 4.8 gigahertz. So if I design a frequency a VCO which operates in this range, I would have output range of 5.8 to 7.2 gigahertz. And okay, and there are advantages of designing a frequency of an oscillator which is different from the output frequency, and that advantage is that the VCO is not going to be pulled in by a blocker. Okay, So I hope you understand why I have chosen a different frequency for VCO than the output frequency. Now I want to design in this frequency range. Okay, let's choose this to be something like 2.4 nanohenry, and this typical number is going to see a series equivalent resistance of something like 2.9 ohms. Okay, and this depends on the process, the metallization and stuff like that, what that loss is. Okay, and then I want to put in here vectors. So basically let's choose a vector. So that's a vector model. Okay, so I'm going to choose these vectors here. Okay, and this sits in an N well, this vector N var. So this basically is grounded. Okay, and this one goes here like this. Now I am going to introduce a control voltage here with a DC feed. Okay, so basically this is a decoupling, and that's a DC feed here, and I can put here a control voltage. So basically source is frequency domain, and I put a control voltage here of 0 volts, let's say. Okay, so this is the control voltage and this is the tank circuit. Now the two sides of this tank circuit, now let's put in some rough number here. These are basically the gate dimensions, and this is basically the array. Okay, so these are the vectors in this process. For example, this is a typical size. Okay, so now what I want to do here is I want to put a bias voltage here. Okay, because these diodes have to be reverse bias. One side of the diode is 0, the other side of the diode has to be fixed, right? So I am going to choose again an ideal choke DC feed, what you call, and I'm going to put them here and here, and they are going to inject a voltage here. Okay, okay, so I'm going to put here two control voltages, sources frequency domain. One voltage is going to be, let's say, 0.95, 0.95. So both sides are basically 0.95 volts. Okay, and on this I am going to do what is known as S-parameter simulation to find out what this tank circuit looks like. Okay, another thing is I don't want to put in current here, right? So I would go here and put here uh, a DC feed, DC block, sorry, for my measurement sake. I don't want to disturb the current here in the tank circuit, right? So to measure this, I am going to put this DC block here and DC block here. Okay, so this is going to give me S parameter simulation. So I'm going to go to simulation S parameters. Okay, and I am going to simulate from 1 kilohertz or 1 megahertz to 10 gigahertz in steps of 10 megahertz, for example. Okay, let's start from 10 megahertz steps of 10 megahertz. Say apply and say OK. So I'm looking at S parameters now, right? So if I simulate this, of course, I have to put the include file, which I forgot. So I'm going to put the include file here. So that's the, of course, so that's the include file. Just 1 second. Okay, so that's the include file, and I'm going to resimulate this. Okay, so now I want to find out the R equivalent. That is going to be real of, okay, again there are no Y parameters, so let me enable Y parameters. So enable Y parameters. So I hope I'm recording. Hello? Yeah, I'm recording. So I am looking at, I have enabled Y parameters on this. So now if I simulate this, I can also put here the equation. Let's put here the equation. Measurement equations. Okay. And here the equation I write for RP. So RP is equal to real of 1 divided by minus Y 1 2, right? Okay, so let's simulate that. Okay, let's see if there is a equation error. No, there is no equation here error. So here RP should be available. So this is RP. Let's look at that. Okay, so now you can see, as I showed you earlier, it is tuning somewhere around 6 gigahertz. Our requirement is 3.8 to 4.8, right? So one way is to increase this value. So let's look at 15 cross 15. Okay, and I simulate this. Now notice this is 1.2K, and if I increase that, it has shifted down from 6 to 5 gigahertz, but look at what happened here. It went from 1.2K to 600 ohms. So I hope you understand what that varactor is doing. Is directly adding to the loss. So let's say this was 3.2 nanohenry, and this was 12 and 12. We'll put them back. So you understand where the loss is mostly coming from. And we have talked about phase noise earlier. Okay, so the same thing I have done, but now see this. It's still 1400, right? And if I just increase the varactor, I have just directly dropped the parallel resistance down to 600 ohms. So you can see what these varactors are doing. Varactors are really lossy, right? But then this inductor also is going to pick up on the resistance, right? So basically this might become something like 3.2 ohms or something like that. Okay, let's simulate this again. Okay, so now we are in the range of sub 5 gigahertz. We have to go from 3 point something to 3.8 to 4.8, right? Now let's target 4.8, right? So are we at 4.8 right now? Yeah, so we are at 4.8 roughly. Marker new. 4.8 gigahertz. Now let's see if I change the control voltage, what's going to happen. So I am going to sweep this control voltage, and I'll call this VC. Okay, and I introduce a variable VC. Okay, and give it a default value of 0, right? And then I'm going to put in here a parameter sweep, and I'm going to sweep VC. So this is something so simple which you can do in ADS, and if you want to do the same thing in Cadence, you are going to struggle unless you are very good with using Cadence. So you can see the small differences which designers face, and the companies are supposed to realize these are the problems the designers are facing. And the Cadence GUI, or basically the whole flow or setup, over 20 years I haven't seen it changing, other than there are some cosmetic changes and something to do with of course the corner sweeps. Okay, other than that it is not as user friendly as what ADS is doing here. Okay, so anyways, and I'm of the opinion that instead of acquiring AWR, they should have acquired Keysight. That would have been much better. Okay, that's another story. Let's go here and put VC and go from 0 to 0.8 and steps of, let's say, 0.2. So I have got, just 1 second. Okay, so now I'm going to sweep the control voltage, and I'm going to have 5 peaks now here, right? Say okay, check and save, and I have to put here the simulation, which is SP1 as the inner simulation, and I would just do simulate. Okay, so now you see I am going from 4.2 to 4.8 roughly, and I barely make the tuning range. But now you can see that my loss keeps above 1K, right? So that means that this is good for phase noise, but the tuning range I'm not achieving. So to improve the tuning range, I can lower this a little. Let's say I want this to be 3.4 or 3.3, and this I want to increase to 14 and 14, and this will drastically bring down the parallel resistance or increase the loss. But I am ready to live with that for the sake of tuning range, right? So now I simulate this again. Okay, I have moved the way in, but you see the RP has gone down drastically. Okay, probably not this much. So let's put 13 by 13. I avoid an odd number, but nothing stops me from being in an odd number. Okay, when I simulate this. Okay, so now I have this one as 800 ohm, is 3.9, and this is 4.7. Again, I don't have the range. Okay, so let's say this is 3.4, and let this be 12, and let this be 12. We were back to where we are. Okay, and I am going to make this as 3.6 again. Simulate this again. Okay, so here is 4.8, and if I put a new marker here, here is 4.4 gigahertz. I want 3.8. So I can sweep to up to 0.9, but then it will become lossy. So here I will go up to 0.9. This is risky because you are forward biasing the diode. Okay, so this is now 4.1. 9. Okay, that's fine. Okay, and this range will slightly go down when you load this VCO. Okay, so when you design for slightly higher frequency, and then basically it's going to shift down. Now you can see the phase noise is going to be worse for lower frequency as compared to higher frequency, because you see that the tank circuit is basically doing this, that RP is lowering. Okay, so I hope you understood what the trade-offs are in terms of tuning range and in terms of phase noise or loss of the tank circuit. Okay, so now I am going to put together a VCO. Now this concept is usually not covered by any of the books or any of the engineers on YouTube I have seen. They don't show you all this because they don't have a mixed knowledge. Basically, they don't have S parameter going along with the analog, right? So I hope you understand why this thing is missed out in most of the treatments in analog integrated circuit books, or the analog integrated circuit designers miss it because they don't mix the RF with the, or microwave with the analog circuit design. And that's the unique thing which I can do because I do both kind of circuits. Okay, now I am going to go ahead and design this. Okay, so I am going to go ahead and design this. Okay, so I'm going to make a new library, and I will call this library as generic PLL. Okay, and I'm going to attach a technology file to this, and that is going to be CMOS 130 nanometer. And I have this over here, and I'm going to say file new, and here I'm going to say cell view, and here I'm going to say is VCO Wi-Fi 6E. Okay, so I'm designing that. Okay, and I am going to create categories here, but later on. So let's create one category at least. File new category, and I will call this as VCO course. So I'm going to make multiple PLLs here to demonstrate to you all the design concepts. Okay, so here I am going to use two PMOS devices. So I'll start with PMOS devices. Okay. Okay, so I'm going to start with MOSFETs, and here I want a PMOS MOSFET, and I am going to choose a current mirror first of all. So I'm going to do 2.5 into 2. So that's the device, and sideways. So that's my first device, and the second device is a large device which is going to be 40 fingers sideways. So that's a 40 finger device over here. Okay, and then I am going to choose 10 finger devices. Now here again, GMP has to be computed if you want to be that precise, and then there are people who just ignore the maths altogether. So we are not ignoring the maths, it's just that I am not doing it for, saving the time. I have already done this kind of stuff, right? So I know that this is 25 micron device. Okay, so this is one here, and I would ask you also to avoid this this what you call trial and error engineer. Don't try to become a trial and error engineer. Okay, there are a bunch of them in this world right now. Okay, so that's your okay, so that's your current mirror, and it sits in its N well. So basically I would be able to do this because it sits in the N well, and then I am able to do this. Okay, and I would be able to cross couple this like this. Course. Okay. Okay. So now I have cross coupled them to give me some negative resistance, and then I'm going to put in an inductor. So if I put in inductor, okay, look at inductors, and I am in an 8 process octagonal inductor, and I want to choose number of turns to be 3, for example, and this one to be 90. So this is 3.2 nanohenry. So if I do 96, this is 3.5 nanohenry, roughly that. And I'm going to rotate this, sorry, put it here like this. Now this one also has a body connection, and you should study the design manual to really see where that body connection goes. That will go to ground, and then there are vectors. So I go here. Let me see if I'm recording. Seems like I'm recording. So I have vectors. Okay, and if you remember what that vector I did was 2 cross 2, no, okay, NVAR 33, that's wrong. Vector RF NVAR, okay, this one. Okay, so this is 2 by 2 micron, 2 by 2 micron, and this is 12 by 12, correct? And again, this process doesn't have a ADS PDK. That's I have done the PDK or fitted the PDK, so the fab will not provide you a PDK, and that PDK is pretty accurate according to me, and we will see now how accurate is accurate. Oh my god, let's do, okay, so here let's rotate this. Okay, so this one comes here like that, and I make a copy of this and rotate it out again. Okay, and this one comes here like that, like this, and we are basically creating the same tank circuit. And of course I like to see the symmetry. Come on. So sorry for wasting your time. Okay, so then I am going to have NMOS, MOSFETs, NMHP. Okay, so here it's 2.5 cross 8, or maybe 4 even, or maybe 6. Let's see if this is going to work. So 1 is over here, and where is that? Other is sideways over here. Okay, now this one is going to P sub, and when we make a block out of this, we are going to have a P sub come out of this rather than directly grounding it. Okay, and this one is connected over here. Oh, okay. Okay, so we have then I have to insert a ground here. Come on, I have no ground here. Analog lip, ground. Okay, so we have a VCO core in here, and I need to put in the control voltage, so I'm going to use a resistance. I cannot have a choke, right? So I am going to go here. Sorry, I'm going to go here and look for a resistor, and this resistance is 600 ohms, and let's say 2 microns. There is hardly any current here, right? So this is 800 ohms, this is 1k. Of course you can break it into series fingers also if you want. Okay, and this is an N valve, so this will go to VDD, of course. So let me just rotate it and put it here. Okay, so now this thing, okay, again this one, this sits in the valve inward, and this one, so all these are basically connected to ground, and this one is connected to VDD. This is N valve, right? So this is connected to VDD, and this control voltage comes here, and then I'm going to use a MIM cap. So I am going to insert a MIM cap. So this is the one which I'm going to use, and I want 0.5 500 femto, or I can put 800 femto. How about 1.2 picofarad? That's okay. And again, this guy would go to body terminal, this one, and again I need similar capacitor for charging and discharging, so I'm going to copy that over here, right? And I am going to make a body connection to supply. So of course I need a startup circuit here, so I'm going to copy this small device over here, right? And I am going to connect this guy to the well, and this guy draws current out of one of the branches, which is this one. This pulls out current to ground, and this guy has to charge from the supply, and this body terminal will go to the supply. Okay, so this is our VCO core, and I want to pull certain current out of this. So I will insert IDC. Okay, VDC, and I want to operate this from 2 volts. Okay, so I'm going to operate this from 2 volts. Sorry about this. Okay, so it's operating from 2 volts. Okay, and let's get this one. Okay, I can put the common ground, doesn't matter. Okay, and then I need a control voltage, so I'm going to put a 0 volts here. So I'm going to copy this. And this control voltage I'm going to set as 0 volts. Okay, so with the voltages we are done. Of course, this will be connected here. Okay, so for voltages we are done. Now we have to pull out a current. So IDC, again, of course there is a relationship between current also, so it's just not the loss. Okay, you can find it in some classic books what the current should be. Okay, so I'm going to put here 300 microamps of current. So that means this one is around 100 micron and this is 5, so it is 20 times the current. So it will be 6 milliamps. I don't know if I require that kind of current, so of course, you know, let me bring it down to 2. Okay, and that current I'm drawing from the current mirror reference. Of course, let me put it here. Fit, let's move this here. Okay, so let me check the connections. The current mirror is going to put current into this, and that current basically is going to divide into 2. There's a startup circuit. These are cross coupled, PMOS and NMOS, sufficient sizes, and if I do a check and save at this point, that's perfectly fine. Right, now I'm ready for simulations, so I'm going to launch the simulator, and here I am going to choose the analysis to be a transient, and I simulate for 200 nanoseconds. Oh, no transient noise. Okay, and then I am going to look at the output. To be saved, select on design. So that's one, and that's another one, and I'm done with that. Let's go back to the, yeah, and I am ready for simulations. So if I hit simulate, okay, first time a little slow. Okay, so I guess did it simulate or didn't it? Okay, it didn't simulate, and I'll tell you it needs a convergence aid. So I'm going to go here and I will go to simulation, convergence aid, initial condition. And I'm going to put the initial condition on this one and on this one, and I'm going to set this node voltage to 0.99 and this one to 0.9. Okay, and I am going to hit simulate again. So let's see, what is it complaining about? Is it complaining something? Warning, nothing special. Okay. Okay, so now let's look at the result, direct plot from main, and I am going to plot this voltage and it is oscillating, correct? And I have to find out the frequency of oscillations. So I am going to go here and I will do a DFT on this one, and I'm going to start from 50 nanosecond to something like 200 nanoseconds, and number of samples I can leave the same or increase it and say apply and say plot. Okay, and then I am going to zoom in. So my machine is slow, I'm sorry for that. So slow. What? Okay, it seems like we have a value. That value is 2.58 gigahertz. How? It's too large. 2.58 gigahertz is too large. Let me see. Okay, so that means that my ADS vectors are not modeled properly. That's only for the proof of concept. Okay, so I am going to go in here and of course escape, and I am going to choose this inductor to be smaller. Let's put 2 turns on this. That's that, and check and save and go back and simulate this guy. And by the way, if you are interested in the VCO core or VCO design, you can refer to my playlist on analog integrated circuit design using ADS. In that playlist you will find a VCO, and also there is a 2-port oscillator method which is used for computing the phase noise. So we will do the phase noise here. We have done the phase noise. I have done the phase noise in that series. Here I'm going to use a PSS and a phase noise option here to compute the phase noise of VCO. Probably in the next, let me see how much time, 1 hour 14 minutes. Probably in the next session I would do that. Let's look at the output here. So this one I can close, and this one I can say reload all windows. Okay, so now this one is 3.84 gigahertz. Again, I can lower the inductor even more, right? So that's kind of strange. Let me see that. 1.8, 1.6 nanohenry. Okay, let's go and change that. Here, let's say if this is Q, and this I make 10 and 10. 10 and 10. Okay. Do I need to touch this? No. Check and save. And I am going to go ahead and simulate this. Simulate. Let's see. Where 6? Where 6.7? 7. 3.8. 3.8. Is it done? File, reload all windows. 4.48 gigahertz. 4.48 gigahertz. Let me see. Okay, now over here. This is confusing. Over here. Q. 8. Come on, what is it doing? 8. Okay. So right now this is 2020. Okay. Check and save. Simulate. .5. Just 1 second. Okay. Okay, probably, few more iterations maybe. Okay, this is 4.87. Let's see if this control voltage was 0.9. Okay, and another thing I want you to check. Okay, here the average value is around 0.9. Okay, so let me go in here. Sorry about that. Q. I'm going to lower this size a little, 2 micron. Q. 2 micron. Okay, so 2 and 2 micron. Okay, and probably this voltage has to be pulled up, right? So anyways, so I'm just going to save this. I'm going to simulate this. Should cross this also. Okay, and then what people do is they put bank of capacitors, and I am not of an opinion, I'm not a big fan of putting bank of capacitors. Of course, if you have to do multiple octaves, you have that option. I usually would prefer to repeat the whole core operating in a different frequency and then mux it out. That way it's going to have a higher Q tank circuit. So that's the reason why I'm not a big fan of that. Let's see what happened here. Okay, lowered a lot. 3.1. We don't want 3.1, right? We want 3.8. So of course this control voltage can be 0.7 or 0.8. Let's look at 0.8. Okay, check and save. And you know why this amplitude has gone down. This amplitude has gone down because the varactors have become even lossier, right, at lower frequency, because the diode is forward biasing and it leaks the current. And I told you in ADS simulation, you know, that's going to happen, right? So one more iteration probably. Okay, and say file, reload Windows, and this one is 3.4. even we don't want that. Okay, so let's go here. Where is it? Q. Let's look at 0.7 and check and save. You can simulate this. So bear with me. Just wanted to tell you, you know, how do you get the tuning range? Of course, when you design something, you design it at a higher frequency, and then when you lay it out, there are certain parasitic capacitances which are going to come in. Again, here I'm not doing any loading here, if you see, right? That would mean that, you know, I should design for even higher frequency. If I was to put here uh, typically 60 femto load, so that's what I'm going to do here. Let me just do this simulation and look at it and say, then I'm going to shift it to a slightly higher frequency. Okay, so this right now is 3.6, so this is good enough. So what I plan to do is I plan to reduce this further, and so that and then I'm going to put in a load here, and that load will be the load of the prescaler. So I am going to insert a capacitor here, and passives cap, come on. Okay, I'll just type here cap. Okay, and this I'm going to keep as 60 femto. This is what my prescaler would be loading it with. 60 femto, 60 femto. So one side is loaded here, other side is loaded here. So everything remains the same. Check and save. And here I'm going to look at the higher frequency limit of 0 volts, right? Tuning voltage of 0 volts. Check and save, and I'm going to simulate this. Just want to make sure that I get the band with the loading, right? Okay, let's see, what do I have here? And this is 5 gigahertz, right? And let's look at 0.8 once more. That's the last time I'm going to see. So I'm going to go here and look at Q of 0.8, and then just hit simulate. Come on. Okay, probably that's my last simulation. So I'm achieving 5 gigahertz on one side, Vc equal to 0. That's 5 gigahertz. And let's look at the other side. Reload. And this one is 3.5 gigahertz. So I'm going from 3.5 to 5 gigahertz. So basically that completes my task. I have designed a VCO core, a startup circuit, properly biased it, and then verified whether I get the tuning range, and I have proved my concept. So I'm gonna stop here. Right, great. See you in the next session.